Welcome dear students, we are on the CEC Gurukul lecture. We are in the series of electronic circuits and in today's series we are discussing the capacitors. Up to now we have discussed what are the capacitors and what is the capacitance inside the capacitor. Now we are discussing how the capacitors are connected in the circuit, in the electronic circuit. We just discussed that the capacitors are connected in the circuit in the series and the parallel manner. In the series manner, here we see on the screen that these capacitors are connected and this is the two capacitors are connected, and then we are having the series capacitance formula. C total is equal to 1 by 1 by C1 plus 1 by C2 plus and so on 1 by Cn. If the n number of the capacitors are connected, it means the C total is less than that of the single capacitor. Now when it is connected in the parallel, then we are having that the C total must be the sum of all the capacitors, like C1 to Cn, C1 plus C2 and Cn. Here we have seen the circuit that the two capacitors are connected, C1 and C2. The total capacitance must be the C1 plus C2. If n are connected, then C total is equal to C1 to Cn. Now capacitor of a parallel plate capacitor is proportional to the area. A measured in the meter square, as we know the area, the unit of area is the meter square of the smallest of the two plates, and then these will proportional to the distance of the separation between these two, that is the dielectric thickness given in the meters between the two conductive plates. So the formula of the generalized equation for the capacitance of a parallel plate capacitor is given as the C is equal to epsilon A by D. A, we know that area, and D is the distance between these two plates. What is this epsilon? Epsilon is represent the absolute permittivity of the dielectric material, which is inside the two plates used as an insulating material. Like the formula is the C is equal to epsilon A by D. A is the area of the plates, D is the distance between them, and epsilon is the absolute permittivity of the dielectric material. Dielectric constant, that is represented by the epsilon naught and also known as the permittivity of the free space. We always discuss that epsilon naught is the permittivity of the free space, and its value is a constant and is given by 8.854 into 10 power minus 12 farad per meter. Free space means air between that. The two plate capacitor, we are having a dielectric, that is the air. So epsilon naught that we take for the permittivity of the free space, and its value is fixed, that is 8.854 10 to the power minus 12 farad or 8.8 picofarad. Now dielectric constant of the free space epsilon, that is represented by naught, epsilon naught, which can be written as 1 by 4 pi into 9 to 10 power 9, may also have the units of picofarad per meter as a constant given by 8.85 for the value of the free space. When we note that the resulting capacitance value will be the picofarad, not in the farad. The value must be having the 10 power minus 12. The conductive plates of the capacitors are separated by some kind of insulating material or the gel rather than the perfect vacuum. So there must be air or some material which is a dielectric inside the two plates. Here on the screen we are having the two plates which are connected with the lead, two wire, and one having the charge Q positive, another having a charge Q negative, and the distance is measured between the two plates defined by the D, and you are seeing that the dotted line, there is a dielectric constant between these two plates, and epsilon is the permittivity of the dielectric. So dielectric with the permittivity, that is represented by epsilon. And left hand side we are seeing that is the conductive plate A, and this is which is connected with the lead, and the conductive plate with the area A in the meter square. We take the area of that is in the rectangular or the square form. And right hand side also we are having a dielectric with the permittivity epsilon in between these two plates, the plate which is also having the area, and that is the conductive plate 2, that is also connected with the lead and having the charge minus Q. So plus Q for the proton and minus Q for the electron. Now when circulating the capacitance of a capacitor, we can consider the permittivity of the air. And especially we are taking the dry air as being the same value of the vacuum as they are very close to each other. So we consider there is a air in between these two plates. Now take the example how we will calculate the capacitance of a capacitor. If we are consider a capacitor which is constructed from the two conductive metal plates, one is having size is 30 centimeter cross 50 centimeter, which are separated by some distance, which is the space between these two is 6 mm, 6 millimeter from each other. Then the dielectric is the dry air in between these two, means the two plates having the dielectric is in between that, and it is only a dielectric material. Then how we calculate the capacitance of a capacitor? Dear students, we know that the formula is C is equal to epsilon naught A by D. First we talk about the epsilon naught, whose values is fixed as we consider the air. Then it is 8.854 10 power minus 12. Then area, which is defined, is the millimeter square. Then we can take the 0.3 into 0.5 m meter square. And D, distance between, is the 10 power minus 3 meter, as we are taking here the 30 centimeter and 50 centimeter, and now which is converted into meter, and the distance between these two plates is 6 mm. So we can convert it into the meter, 6 into minus 3 meter. Then the C, the capacitance of a capacitor, we calculate it is equal to 0.221 nanofarad. Means if we calculate it is 221 into 10 power minus 9 farad. So this is the capacitance of a capacitor. This is a formula to calculate the capacitance of a capacitor. Now another, which is a very important, as we are talking about all the dielectrics in between the two plates, then what is this dielectrics of a capacitor? What is this dielectric, and what is the use of this dielectric between these two capacitors, and how we calculate the permittivity of these dielectrics, how we take the permittivity of dielectrics, because it is an important part between the two plates of the capacitor, in the capacitor also. As well as overall size of the conductive plates and their distance spacing apart from each other plays very important role in the calculating or the changing the value of the capacitor. But dielectric constants also affects the overall capacitance of the devices. The dielectric material which is being used must change the value of the capacitor. Or we can say that the factor which affects the overall capacitance of the device is the type of dielectrics materials being used in the capacitor. And in other words, the permittivity of the dielectrics, means dielectrics we are using, so we take its permittivity. So permittivity is also plays an important role in the changing of the capacitor, in the capacitance of the capacitor. So next we take the conductive plates of the capacitor, and generally made of the metal foil and the metal film, allowing for the flow of the electron and the charge in between these two plates. But the dielectric material used is always an insulator. The various insulating material used as a dielectric in the capacitor differ in their ability to block or to pass the electric charges in between these two plates. So this is a very important role of the dielectrics between the two plates. So this dielectric material can made in number from the insulating materials or the combination of these materials, with most common type of used being air, paper, polyester, polypropylene, mylar, ceramic, glass, oil, air, or a variety of the other material, but it must be the insulating material or the mixture of the materials, combination of these materials. The factor by which the dielectric materials or the insulator increases the capacitance of the capacitor compared to the air is known as the dielectric constant. Dielectric constant, that is represented by the K, and the dielectric material with a high dielectric constant is better insulator than a dielectric material with a lower dielectric constant. What we are saying, that the dielectric material with a high dielectric constant is a better insulator when the value of the dielectric constant is more, and it's a better insulator, work as a better insulator than dielectric material which has a lower dielectric constant. It means it is having a high dielectric constant, that is a good insulator. The dielectric constant is a dimensionless quantity since it is related to the free space. And then the actual permittivity or the or the complex permittivity of the dielectric material between the plates is then the product of the permittivity of the free space and the relative permittivity of the material being used as a dielectric, and it is given by epsilon is equal to epsilon naught into epsilon r, that is a complex permittivity. So how we calculate the complex permittivity? That will be the actual permittivity, that is the actual permittivity we calculate by taking the product of the permittivity of the free space and the relative permittivity of the material which we are using, which are using as a dielectric in these two plates. So epsilon is equal to epsilon naught into epsilon r. The permittivity of the free space epsilon, our basis we make equal to the 1 because we are taking the air. When the vacuum of the free space is replaced by the some of the other type of the insulating material, their permittivity of the its dielectric is referenced to the base dielectric of the free space, giving a multiplication factors known as the relative permittivity, that is represented by epsilon r. So the value of the complex permittivity epsilon will always be equal to relative permittivity of times 1, that will take the epsilon is equal to 1. The typical unit of dielectric permittivity epsilon or the dielectric constant for the common material, if we take the pure vacuum, that is the 1. If we take the air, that is the exact value 1.006, but we consider it as a 1. For the paper, it is 2.5 to the 3.5, in between 2.5 to 3.5. For the glass, it is in between we are talking about dielectric permittivity. For the glass, it is 3 to 10. What type of glass we are using? Mica, the permittivity in between the 5 to 7, and wood from 3 to 8. Metal oxide powder 6 to 20, etc. Means what type, how much capacity we require in the capacitance, on the basis of that we choose the dielectric constant. This then gives us the final equation for the capacitance of a capacitor as defined as C is equal to epsilon naught epsilon r A divided by D farad, that's units of farads. In the previous we are having a C is equal to epsilon by A by T, but here we talk about the precise value, or we take the dielectric permittivity, then the capacitance defined as the epsilon for the air, epsilon r for the material, A area of the plates, D divided by the distance between these two plates, that is the capacitance formula. One method used to increase the overall capacitance of the capacitor while keeping the size small is to interleave more plates together within a single capacitor body. This is another factor to increase the capacitance of a capacitor, means we interleave the more plates into the capacitor devices instead of just one set of the parallel plate capacitor. A capacitor can have the many individual plates connected together, thereby increasing the surface area A of the plates, and as we increase the surface area, then the capacitance will increase, because in the formula we have C is equal to A by D. Distance should be small, A must be greater. So if we increase the surface area, then the capacitance will increase. So if anyone asks question, then you can give the answer, how can increase the area. Surface area is also one of the factors, so if we take the multiple plates, then we can increase the capacitance of a capacitor. For a standard parallel capacitor, we also define the capacitor has the two plates labeled by A and B. Therefore, as the number of the capacitor plates is 2, then we have N is equal to 2 and represent the number of the plates. Then here, then our equation about the single plate capacitor should really be C is equal to epsilon naught epsilon r n minus 1 A divided by D, that is in this farads. Now you see on the screen, here is we are having a multi-plate capacitor to increase the capacitance of a capacitor. So 5 plates are connected to one lead A and another point B, another lead point. One is positive and another is a negative terminal. B is the negative and A is the positive terminal. Then both sides of the 4 plates connected to the lead B are in the contact with the dielectrics. All are dielectric in between these two. This is a multi-plate capacitor. Dielectrics are in between these multiple plates, and here we consider the two individual plates. One is the A, which is having in multiple plates, and another is B, is another multiple plates, positive and negative charge on these plates. So 5 plates are connected to the one lead and the 4 plates are connected to the another lead, and they are both are placed together, and then the both sides of the 4 plates connected to lead B are the contact with the dielectrics. Again you are seeing there is a space between these two plates and the dielectrics in these plates. So 8 mm capacitor is the one here, whereas only the one side of the each of the outer plates connected to the A is in the contact with the dielectrics. We see there one side of each of the outer plate connected to the A is in the contact with the dielectric. Then as above, the useful surface area of each set of the plates is only the 8, and its capacitance is therefore is given by, you see here on the screen, as the for the single plate capacitor n is equal to n minus 1, that is represented by the 2 minus 1, which is equal to the 1 as we take the single plate capacitor, and C must be epsilon naught epsilon r into 1 into A by D is exactly the same as the C is equal to epsilon into epsilon naught epsilon r A divided by D, which is the standard equation. Here we see, as we are talking about the n is equal to 9, you see that here with the 9 capacitor, so you can C is equal to epsilon naught epsilon and n minus 1 A divided by D. So we take the 9, so 9 minus 1 A divided by D, it will be epsilon naught epsilon r 8 A divided by D. Now area and the distance between these two plates we have. So this formula is for the multi-plate capacitors, and the value will be changed as we change the number of the plates connected in the one lead. So this is for the multiple lead. Now suppose we have the capacitor made of the 9 interleaved plates, then n is equal to 9, then the formula will be epsilon. If it is a 7, then we can add epsilon naught 7A divided by D. In this manner the capacitance will change. The modern capacitors can be classified according to the characteristics and the properties of their insulating dielectrics. It means the capacitors capacity is defined by the, or is the characteristics defined by the insulating dielectrics inside it. Low loss, high stability such as mica, low K ceramic, polystyrene, the many researchers going on to get the high capacitance in the capacitor. Medium loss, medium stability such as a paper, plastic and film, and high K ceramics. Polarized capacitors such as electrolytic and tantalums, they are the basic capacitors. So that the another factor which affect the capacitor is the voltage rating of a capacitor. One was the dielectric and another is the voltage rating of a capacitor. All the capacitors have a maximum voltage rating, and when we are selecting a capacitor, consideration must be given to the amount of the voltage to be applied across the capacitor is also one of the factor. The maximum amount of the voltage that can be applied to the capacitor without damage of the dielectric material is generally given in the data sheets. That is the working data, that is the DC or the DC working voltage. So voltage rating of a capacitor, if we take the voltage applied across the capacitor becomes too great or too large, the dielectric will break down and it will not work down. If the voltage applied is larger, then dielectric will damage, known as the dielectrical breakdown, and arcing will occur between the capacitor plates, resulting in the short circuit. Sometimes it will damage the capacitor. The working voltage of the capacitor depends on the type of dielectric material being used and its thickness. So on the basis of the dielectric we are choosing, on the basis of the thickness of that material, the dielectric, then we use the applied voltage. So voltage rating plays an important role in the capacitor. Now the DC working voltage of the capacitor is just that the maximum DC voltage and not the maximum AC voltage as the capacitor with the DC voltage rating of the 100 volts, DC cannot be safely subjected to an alternating voltage of the 100 volts. Since the alternating voltage, that is the value of 100 volts, will have the peak value over the 141 voltage, that is root into 2 into 100. It means when we apply the voltage across the plates, then we have to be careful, and it must be based upon the dielectric constant which we are using. Then the capacitor which required operate at 100 volt DC and should have working the voltage at least 200 volts. So the pre-data we are having, on the basis of that we can apply the voltage. If the capacitor is required to operate 200 volts, then we apply the 200 volt AC. In the practice, a capacitor should be selected so that its working voltage, either DC or AC, should be at least 50% greater than that of the highest effective voltage to be applied to it. Another factor which affects the operation of the capacitor is the dielectric leakage. Sometimes there is a leakage in the dielectric. Sometimes, what is this dielectric leakage and how it occurs? The dielectric leakage occurs in the capacitor as the result of the unwanted leakage current which flows through the dielectric material. Means sometimes there must be damage in the dielectric material, or there must be a doping material is not properly, and the leakage of the current takes place in the dielectrics. And it means the leakage of the dielectrics plays also the affect the operation of the capacitor. As capacity will storage capacity will be lower if there is a dielectric leakage which flow through the dielectric materials. The work of the capacitor is to store the electric charge onto its plate. The amount of the electrical charge that the capacitor can store on its plates is known as its capacitance value, and depends upon the three factor. As we are discussing from the previous, that the capacitance of any capacitor depends upon the three main factors, or the working of the capacitor to store the electric charge between these two plates. So what are these factors? Number one factor is the surface area. The surface area, what is the surface area of the plates? The surface area of the plates. The surface area A of the two conductive plates which makes up the capacitor. The larger the area, the greater is the capacitance. So one factor is the surface area. If surface area is more, the capacitance will be more. Second is the distance between the two plates, two conductive plates. So distance plays an important role. If the distance is small, then the capacitor is greater. So distance represented by the D between these two plates, the smaller the distance, the greater is the capacitance. The third important factor is the dielectric material. The type of dielectric material which we are using to separate the two plates, that is called the dielectric. The higher the permittivity of the dielectric, the greater is the capacitance. The higher is the dielectric constant, the greater is the capacitance. So these are the three factors which define the capacitance, or which affects the capacitance of a capacitor, or the storage capacity of the capacitor. So one is the surface area of the plates, two conducting plates which we are using. Second is the distance between these two plates, and third is the dielectric material between these two plates. So we have to be careful to choosing this, and on the basis of that we can construct a capacitor by taking these three parameters into the account. So capacitor can be used of many different applications in the circuits, electronic gadgets. In the electronic gadgets we use a capacitor. So capacitors can be used in many different applications in the circuits, such as the blocking the DC current while passing audio signals, pulses, or alternating current, or other time varying waveforms. The ability of block the DC current enables a capacitor to be used to smooth the output voltage of the power supplies, to remove the unwanted spikes from the signals that would otherwise tend to cause the damage or the false triggering of the semiconductor or the digital components. So sometimes we use to remove the noises. So capacitors can also be used to adjust the frequency response of the audio circuit, or to couple together, separate the amplifier stages that must be protected from the transmission of the DC current. So here we just have the many applications of the capacitor. You all know that this without any circuit is not complete without the capacitor. So most of the time we have used the capacitor in developing the or in installing the electronic gadgets. So capacitors plays a very important role in the electronic circuit. Thank you very much.